This is our review of parallel circuits. Okay, I don't mean to think you guys don't remember this, but this is one of those skills, this is one of the basic things you need to know. All right, that's why I put it in the review packet. So in the review packet, you see a worksheet like this. Okay, remember there are basically 3 formulas for calculating parallel resistance. Okay, so you can use this one. Okay, it's the product over sum method. I don't use this one very much. I find it to be a pain because I like getting things done just like you guys do, especially when I got the calculator. All right, so I don't use the product over sum. Remember, product over sum is when you have any 2 resistors. You can use that formula to figure out total resistance. It works. What if all your resistors are the same value? So you got 2 10-ohm resistors in parallel. Well, if they're the same, okay, remember, if you have the same value resistors, you can use this formula, the equal value resistors in parallel. You take whatever the resistance is and divide it by the number of resistors. So if I have 2 10-ohm resistors in parallel, 10 divided by 2 means my total resistance is 5 ohms. Okay, now wait a minute. Some people are going to sit there and think, wait a minute. I have 2 10-ohm resistors in parallel, but my total resistance is 5. Okay, what if I had 3 10-ohm resistors in parallel? 10 divided by 3 is 3.3, right? How come my resistance keeps going down? Okay, what if I put 4 10-ohm resistors in parallel? 10 divided by 4 gives me 2.5 ohms. Why does my resistance keep going down when I keep adding resistance? Remember, when I went over this unit, I talked about highways. If I want to drive through Warren, and I'm going to be stuck on Pennsylvania Avenue, and I need to go from the east end to the west end of Warren on Pennsylvania Avenue, that's a series circuit, right? There's only one path for me to go from one end of town to the other. And if you have one slow car, one big resistance in the way, it's slowing everybody down, so in turn you have more resistance. So how does parallel compare? Well, parallel is kind of like having a big interstate, like Washington, D.C., when you have 4 or 5 lanes of traffic going one direction. Okay, you got a lot more resistance there, there's a lot more cars. But if somebody's in your path, you can switch lanes, just like electrons are going to do. So by adding resistors in parallel, you're actually decreasing resistance because you've just opened up more lanes of traffic. More lanes of traffic, like I'm not stuck on Pennsylvania Avenue anymore. I'm on a 4-lane highway trying to go from the east end of Warren to the west end of Warren. I'm going to get through Warren in seconds, okay, because those lanes are in parallel. So adding resistance in parallel actually decreases resistance. And then we have the formula where when you have all kinds of different resistors, this is the formula you need to use. Now, the way we do it in here, in fact, let me hit my light. If you guys don't forget, or if you did forget, we put it in a calculator like this. We do the resistor, resistor 1. Hit that reciprocal button. The button on a calculator looks like this. The reciprocal button. You want that one. So that's the one I like you guys to use, right? So you put your resistor in there, hit reciprocal plus, second resistor, reciprocal. Make sure you use parentheses, and then your last reciprocal goes right there. That's the one I suggest using most. So. All right, let's swing this camera around, and we'll do 2 different problems from the worksheet. We'll do 2 of them. Make sure you guys remember how to do parallel circuits. Okay, we'll swing this thing around. Okay, we're going to do these 2 problems here. All right, we're going to do them over on the board over there. So I need you to look at worksheet that says Parallel Practice 2.7. Okay, Parallel Practice 2.7. We're going to do this one first. The one that has 45, 90, 30, and 45 ohms with a voltage supply of 45. Once we get done with that one, we're going to do the second one on here, which is really about as complicated as they get. So we'll do these 2 problems, and we'll call this video quits. Okay, so again, we are on Parallel Practice 2.7. Let's do this one. All right, so What was the one thing you were supposed to remember about circuits in parallel? All the voltages are the same, right? It's just like the outlet in the front row here, okay? You found one of the voltages, 120 volts, right? Well, it doesn't matter what the resistance is sitting next to that one. Like you got two different lamp plugs in, like maybe one's running a incandescent light bulb, one's running LEDs. They're still hooked up to 120 volts. Okay, it doesn't matter what each one is drawing. So remember, in parallel, all your voltages are the same. Okay, so obviously on your worksheet then, I already gave you the fact that you have 45 volt power supply. So you can go through and write on your worksheet, fill in E1 is 45 volts, E2 is 45 volts, E3, 45 volts, E4 is 45 volts. So you got your voltages done. Voltages in parallel, always the same. So then we need to come down, we need to get all these currents finished, right? So again, you need your calculator app. So how do you get your currents? E divided by R gives you I. So it's 45 divided by 45. We don't need a calculator for that, right? The current flowing right here, 1 amp. So I1 is 1 amp. Okay, we need I2. 45 divided by 90. Should be an easy one, right? 45 divided by 90. Probably going to give you half an amp or 500 milliamps, right? What about 45 divided by 30? Should be 1.5 amps, right? 45 divided by 30, 1.5 amps. Okay. And finally, 45 divided by 45, you have another 1 amp. So you have your four currents now. I1 is 1 amp, I2 is half an amp, I3 is 1.5 amps, I4, 1 amp. What's my total current? Here's the other thing to remember. Kirchhoff's current law. So remember, in series circuits, Kirchhoff's voltage law, the sum of the individual voltages must equal the applied. What about Kirchhoff's current law up here? Kirchhoff's current law says the individual branch currents must equal the supply current. Okay, so Kirchhoff's current law, the individual branch currents must equal the supply. So if you take one, 1.5 here, 1.5 here, well, looks like you got 3 amps there plus 1. Looks like my total current again is 4 amps. So we got 4 amps flowing. So that's IT is 4 amps. Okay, we didn't even go through and calculate total resistance on this. Now, there are two ways to do this. We could make this easy, or we could just double check ourselves and do it both ways. So, let's look at this. So with your calculator, when you do the reciprocal method, so here's our resistances, right? So one other thing to remember about circuits in parallel is we have a 45, a 90, a 30, and a 45. Your total resistance is always going to be smaller than the smallest resistor. So when you see these four that are in parallel, smallest one is 30. My total resistance had better be smaller than 30 or we did something wrong. Okay, so what I want you to put in your calculator is this. Parenthesis. You're going to put this 45 in. You're going to hit that reciprocal button. Looks like this. All right, the reciprocal button. I'm going to hit plus. I'm going to put this 90 in. Reciprocal. I'm going to put 30 in. Reciprocal. Put that last 45 in. Hit reciprocal. Close the parentheses. Hit reciprocal again. What do you get? Well, let me plug it in here so I can show you what I did. So parenthesis 45 reciprocal plus 90 reciprocal plus 30 reciprocal plus 45 reciprocal. Close the parentheses. Hit reciprocal. Now, does that show up on there? Yeah, I think it kind of does. There we go. So it says our total resistance 11.25. So RT is 11.25 ohms. Now let's double check that. Let's double check this number. How do we double check it? Well, we say my total voltage is 45. My total current is 4. E divided by I should also give us this. So if we take our calculator and do 45 divided by 4, same thing, did it right. Okay, so there's my total resistance. What about my total power? How do I do total power? Well, Watt's law, right? P equals I times E. So what is 45 times 4? 45 times 4 equals 180 watts. So on your paper, the total power is 180 watts. 180 watts. So let's go through and find each individual power. If I can find a marker that's going to work. So P equals I times E, right? Well, the E's are all 45, so all I got to do is multiply here, right? So E and I, so that means P1 is going to be 45 watts. 45 times 0.5, so what's half of 45? 22.5, right? What is 45 times 1.5? I believe it's 60, right? No, I was wrong. What was I thinking? I don't know why I was thinking 60. Yeah, because, yeah, that doesn't make any sense. So, P3 is 67.5 watts. 67.5 watts. I really need to get my marker to work. And again, 45 times 1 means P4 is 45 watts. So again, P1 is 45. P2, 22.5. P3, 67.5. P4 is 45. Okay, so hopefully these all add up to my 180. Looks like they do. So, again, with circuits in parallel, voltages are always the same. Kirchhoff's current law is the sum of the individual branch currents must equal the applied current, right? And when you have resistors in parallel, whichever one of these is the smallest, your total is going to be smaller than the smallest resistor. If for some reason you did this and you ended up with a 32 ohm total resistance, a bell should be going off saying, woohoo, hey, something's wrong here, fix me. So that's parallel circuits. Actually, no, it isn't. I want to do one of the more complicated ones on 2.7. Let's do the next one down. So we'll pause the video here for a second and I'll get this drawn. Last one we're going to go over for the parallel video. This is the second problem on worksheet 2.7. Okay, the one just below the one we just did. This one's a little more complicated. As you can tell, we only have one resistance value. We only know R1 is 7,500 ohms. We don't know what R2, we don't know what R3 is. We don't know what our total voltage is. So this one's a little more complicated, why I picked this one to do next. But we do have enough information here to figure this out. All right, so we need to start with where we can start. We can't just, make things happen. So, I mean, we got to start with a piece. You can't eat a pizza in one bite. You got to break it down to manageable pieces. So, first thing we can do, I need my green marker, is we have a current, okay? It says on your paper 0.0316 amps, which is 31.6 milliamps. And that is flowing through the 7,500 ohm resistor. So, using Ohm's law, if you take your current and you multiply it by your resistance, you're going to get the voltage. So if you plug that in your calculator, you put 0.0316 times 7,500 ohms, you're going to get 237 volts. So, what's the same in parallel? Voltages are the same in parallel. So we just found all the voltages. We found our total voltage. We found this voltage. All of these are 237 volts. So that works. That gives us another piece of the puzzle, right? Well, actually, we can come up with total resistance now, right? Because we have total voltage. We know total current. Total current on your paper should say 0.0632 amps, which is 63.2 milliamps, right? So if we do E divided by I, take your calculator, take that 237 you just put in there, and divide it by, I'm going to divide these two. 237 divided by 0.0632, hit equals, get something like that, 3,750 ohms. That's my total resistance. 3,750 ohms. So we know RT and we don't even know all the resistors yet. Okay? So let's go with what we have. If you look at your worksheet, which I have over here so it's convenient for me to look at it, it says that we have P2. Right? We have P2 here, but we don't have any current here, so there's nothing I can do really here, is there? Okay. So what can I do? What can I do next? I do know that we have 237 volts, right? I mean, I do know that. So, I mean, I don't have the resistance. Over here, I have 237. I don't have a resistance, and I don't have a current. So, I guess I can't. I can't do anything here, but I can do something here, right? So, I have power and I have voltage. So, if I take power divided by voltage, right, what are you going to get? E divided by E gives you I. So, let's figure that one out. So, my power is 4.6, should have been reading glasses on. 68075. So we took 4.68075. We're going to divide it by 237. Probably going to be a small number, and it is. Right? Very small number. Now again, hit the ENG button. The ENG button will move that over for you. Okay, so we have 19.75 milliamps. Actually, I want to write that in red, keep all my colors consistent here. So 19, that's I2, 19.75 milliamps. We know that current. Probably can find resistance now, right? How do you get resistance? E divided by I will give me that resistance. That's black. Where's my other marker? I guess that one will work. So we need to take our voltage divided by our currents. We're going to do 237 divided by 19.75 exponent negative 3 equals like 12,000 ohms, right? So this is 12K. It's 12K. How do we get the one that only has one value? How do we get that? All we have is 237. We don't have a resistance. We don't have a current. We don't have a power. Nothing going on here. Let's think about this. If my total current, remember Kirchhoff's current law. Kirchhoff's current law is the sum of the individual currents must equal the applied current, or the sum of the individual branch currents must equal the applied. So I know that we have 63.2 milliamps. This guy is using 31.6 milliamps. This guy is 19.75 milliamps. So if I add these two currents, these two here, add these two currents and subtract from this one, I better get this one. All right? So we'll do that. Actually, we'll take 63.2, because these are milli, and we'll subtract 31.6. And we'll subtract 19.75, because everything's in milli. We end up with 11.85 milliamps for this one. Yep, that's red. So now Kirchhoff's current law, we add these three currents, we get our supply current. Now we can keep going with this. So we know voltage, we know current. If I divide these two numbers, I should get that resistance. So we're going to take 237, divide it by 11.85 exponent negative 3, because it's milli. Don't forget that milli, you'll get it wrong, exponent negative 3. All right? Since we got 20,000 ohms. Okay, we just need some powers, right? Pretty much got this thing taken care of. We just need some powers. So, how do you get power? P equals I times E. So we're going to multiply these two to get this power. We're going to multiply these two, right? Get that power. We're going to do our total voltage and our total current here to get that power. So let's start off with total power here. So we're going to do 237 times, and this current here. So if I do 63.2 exponent negative 3, my total power is right there. Okay, it's 14.9784 watts. All right, let's do this one. So again, we'll do 237 times 31.6 exponent negative 3. Get about 7.48 watts. Okay, so that's going to be P1. That's P1. Looks like an R. P1, 7.4892 watts. 7.4892 watts. One left. 237 times, right there, 11.85 exponent negative 3. Get about same thing I got there. I can't read it on the screen here. 2.80845. Yep. Because my camera, the thing's backwards. Not used to this. So power 3 is 2.80845 watts. And that finishes it. That's it. So again, in parallel, as a reminder, all your voltages are the same if you're in parallel. Kirchhoff's current law says these branch currents must add up to your total current. And again, your total resistance, look at this, 7,500 ohms, 12,000 ohms, 20,000 ohms. You get 20,000, 12,000, 7,500. But my total is 3,750 ohms. So if you get some answer that is larger than 7,500, you know you did something wrong, because your total resistance is always smaller than the smallest resistor. So, other than that, you can see our power's added up to the total power. So that's parallel. That's parallel circuits. So hopefully this is working out. This is a good review for those that need the review. Some of you probably don't even need it. So we'll get these posted up on the wcccelectronics@gmail.com. Okay, the coat thing. I'm not wearing it because I'm some kind of professor. I'm wearing it because it's cold in here and it's snowing outside. So, all right. Hey, we'll talk to you guys later. I think I got to get out of here. As a matter of fact, we're redoing. I put my kids to work. They're doing all kind of electrical work. We're rebuilding our audio and our electrical system at the church I go to. So I got to get there. We got some YouTube videos to make for our Sunday service. So, okay, we'll talk to you guys later. Samson out.